So, okay, welcome to the fifth meeting of our algebra seminar, and today we have Christopher Dean, who's gonna talk about globular multi-categories with homomorphism types. And I'm sorry if we had a bit of technical issues today. Now I will mute everyone, and if someone wants to ask something, they can unmute themselves and speak. So Christopher, you can start whenever you want.
Great. Thanks very much. And thanks for the invitation. So my name is Christopher Dean, and I'm finishing off a PhD at Oxford at the moment. And I want to talk to you about some structures called globular multi-categories with homomorphism types, which I think turn up fairly naturally whenever you have a collection of higher category-like objects, or very frequently at least, or whenever you have some sort of directed type theory of homomorphism types, you should get one of these structures, and hopefully I'll convince you that they're quite useful. Right. So the starting point for this work is really this paper by Benno van den Berg and Richard Garner called Types Are Weak Omega Groupoids. What they do is they start off with the type theory with identity types, and then they construct, using the tower of identity types that I've illustrated at the bottom. Given any such tower of identity types inside a type theory, we expect that that tower should have the structure of a weak omega groupoid. And van den Berg and Gardner make this precise as follows. They start off with a type theory. As an intermediate step, they construct a monoidal globular category. And then they show that there's a globular operad which maps into that monoidal globular category, picking out that tier of identity types. And that globular operad is contractible. And so this result says in a precise way that the tower of identity types has the structure of a weak omega category. And then you can show it's a groupoid afterwards. So what I would like to do is to sort of understand what's going on in this paper. So I'll proceed in two steps. Firstly, I'll try to understand the image of the first functor to monoidal globular categories. I'll actually work with globular multi-categories, but they are to monoidal globular categories what multi-categories are to monoidal categories, so you don't really lose very much, and things work well. So I'll look at the image of that first functor, and we'll see that when you have a globular multi-category, you can ask for an extra structure on it called a homomorphism type. And you always have these homomorphism types whenever you start off with anything like a type theory with identity types. As a second step, once we have a globular multi-category with homomorphism types, I'll show that there are lots of nice higher categorical structures that you can construct. So you can do more or less what van den Berg and Garner do and get a tower of identity types for every type. But there's more that you can do. You can actually look at the terms in the type theory that you start off with and construct higher functors between those higher categories. And the dependent types actually behave like higher profunctors. And in general, there will also be terms that are transformations between profunctors and that sort of thing. So those are the two parts of this talk, really. So a definition, a globular multi-category consists of two globular sets, a globular set of types, and a globular set of terms. And the terms have a kind of multi-category-like composition. So let's look at those two things in detail, and I'll introduce some terminology. So first, the globular set of types. We'll call the 0 cells 0 types, and the n cells n types, and so on. And we'll depict these cells as follows. So we'll just depict 0 types by points, and 1 types as horizontal arrows between 0 types. And 2 types are then globular cells between 1 types. And I would encourage you to think of these types as corresponding to type theoretic judgments like these ones on the right. The globular set of terms is more interesting. The terms in general are sort of generalized multi-category like arrows. So a term is going to take a globular pasting diagram of types in the sense of botanin, and then output a single type. So you take in something complicated, a pasting diagram, but then it's a multi-category like thing, so you only output a single type. So let's look at what those are in low dimensions. Zero terms are quite boring because there aren't any interesting zero-dimensional globular pasting diagrams. So the only zero terms take a single zero type and output a single zero type. So we just denote them by vertical arrows. Or very simple deductions in type theory. The one terms are more interesting. So now we're going to take a one-dimensional globular pasting diagram and output of one type. Well, a one-dimensional globular pasting diagram is a list of one types. So I've drawn two typical examples of one term here. The first one takes a list of length 2, and it outputs a single one type. I should say that every one term has two boundary zero terms. As you can see, they're G and H in these pictures. And a typical example of this top type of term, which corresponds to this kind of judgment in a type theory, is the term in a type theory which takes two composable paths and composes them. This bottom one term takes the one-dimensional pasting diagram, which is just a zero type. And in a sort of type theory way, what that does is it takes an element of that zero type and it outputs an element of the one type. The classic example of these kinds of things are actually natural transformations. So you take, if you have two functors G and H from A to D, and in this case D and E are the same. You have two different functions, and then a natural transformation takes a single object here, and then it outputs an arrow between these two inside this output category. Okay, I'll draw two terms. That's as high as I'm going. That's the limit of my artistic ability. But just to give you some idea of what's going on. So a typical two-term has source and a target one term at the front and the back in this picture. And it takes a two-dimensional pasting diagram to a single two type. Or alternatively, we can use this type theory notation. Great. Our terms have a sort of associative and unital composition, which says that whenever we build up pasting diagrams out of these shapes I've been drawing, we can compute a composite with the same boundary. And the way the units work is kind of multi-category like, so you just plug in identities into all the inputs on that side. So here's an example that hopefully justifies the terminology. Every dependent type theory induces a globular multi-category where the types in the type theory are exactly the types in the globular multi-category, or the dependent types in the type theory, the dependent types in the globular multi-category. And the terms are then terms and dependent terms in the type theory as well. But where we restrict the contexts vary quite a lot, so that the contexts have to be globular pasting diagrams. Here's another useful example. If we start off with a category with pullbacks, then there's a globular multi-category span C whose types are spans and spans between spans and spans between spans between spans and so on in C. To understand the terms, well, the simplest sort of terms are just going to be natural transformations between spans. But more generally, if we have some globular pasting diagram of spans, we'll first have to compute its limit using a bunch of pullbacks, and then look at transformations from that to understand what the terms are. And we don't necessarily have to look at all the spans. Often we would like to restrict our attention to a specific class of spans. And typically the spans we're interested in are the ones that behave like two-sided vibrations. So in the paper of Vandenberg and Garner, which I mentioned earlier, this is basically what they do. They start off with a category with a notion of path object, and then they look at the spans whose legs are vibrations. Lots of familiar examples can be seen as low-dimensional globular multicategories. So the one-dimensional analog of a globular multicategory turns out to be something called a virtual double category. And virtual double categories are to pseudo-double categories what multicategories are to monoidal categories. So every pseudo-double category will give you a globular multicategory. And the kinds of examples of double category that I would encourage you to think of are the examples where the objects of these double categories are category-like things. So they may be ordinary categories, but they may also be some sort of enriched or internal analog. That's fine too. So those will be our zero types. Our one types will then be the correct notion of profunctor. Our zero terms will be functors, and our one terms will be transformations between those profunctors. And so really what we want to do with globular multicategories is to think of their objects in general as being not just category-like, but higher category-like. That's the kind of intuition that I have about globular multicategories and that I'm trying to generalize from the low-dimensional case. So as a first example, you can construct a globular multicategory whose zero types are strict omega categories, whose one types are profunctors. Two types are then things I call profunctors between profunctors. So if you think about what a profunctor is, it's a functor that outputs a category. So if you have two of them that output two categories, then you can then look at profunctors between those output categories. The zero terms are functors between strict omega categories, all strict in this sense. And the higher terms are transformations. So this is all the strict case. I would expect this to work in a sort of semi-strict case as well, but that's each work. So to summarize, we have all these kind of familiar collections of category and high category like objects, and we can always organize them into globular multi-categories. We can either start off with a type theory, or we can start off with something maybe more from category theory. And these things that we start off with in category theory really are kind of directed in their flavor. In the type theory, you know, we are used to considering undirected identity types, but down here we have like not just omega groupoids, but general omega categories and directed things between them. So this work really is supposed to provide a good context to talk about the type theories with homomorphism types. So they're the type theories that also have this directional flavor. So the next thing I want to do is to pin down a bit more about what sort of globular multicategories can appear from these sorts of functors. There's some extra structure that all these starting objects have, which is they have some starting structure that looks like an identity type or a homomorphism type. So in the type theory, we have identity types. In this kind of omega category case, the analogous thing are the Hom profunctors between higher categories. And those behave kind of like directed identity types in a sense that I'll now make precise. So what we're going to do is we're going to look at the identity types here in the type theories, and then we're going to see what they look like from the perspective of a globular multicategory. We say that a globular multicategory has homomorphism types when for every n type A, there's an n+1 type, which we think of as the homomorphism type of A. So I've drawn some pictures of, just adding an n type whose source and target is an n+1 type whose source and target is A. And there's a canonical term associated to every n type as well, which we think of as a reflexivity term. And it goes from A to its homomorphism type. So here's how we might depict the reflexivity term of a zero type A, and here's me attempting to draw that for a one type M.
Sorry, one question in the previous slide.
Yep.
Maybe one example. In the case of the category of profunctors, which to my understanding induces a globular multi-category, do you have homomorphism types?
Yes, so the homomorphism type in that case is going to be the Hom profunctor, and the reflexivity term is going to be the thing that picks out the identity arrows.
Okay, thank you.
Yeah, good question. Right. So now that we have these identity types, these homomorphism types, if we start off with some globular pasting diagram of types, so I call those contexts, then we can start to add in those homomorphism types into a context. So if we start off with a pasting diagram like this on the left, and then we choose some low dimensional element, say A, and then we add in a homomorphism type at A, and you will get a new diagram of types that looks like this. But we could also start off with something like M and add in a homomorphism type, and we get a different shape of globular pasting diagram. And if you think about what the defining properties of identity types in type theory say, they say that we can always freely add and remove identity types from contexts, as long as we know where the reflexivity terms go. So let's make that precise in this sense. So let f be an n term, and choose just an n-1 dimensional variable x to start off with, so a point in this kind of picture on the right. If we add a homomorphism type at that point, then there should be a new term, right? Because we just defined this term such that when we substitute in the reflexivity term of that point, we get back f. So this is the simplest case, but in general, we actually want something slightly more complicated. If x is not an n-1 dimensional variable, but is actually, that should be k less than n-1, a k variable, then if we start off with a term like this on the right, and suppose we add in a homomorphism type to the source pasting diagram of this term at the top, well then the new term that we're interested in will have a source and a target n-1 term that also have that added identity type in their source and target in their context, source context. So rather than just taking a term f and a variable x, we need to start with a term f and a variable x, and also some data that says what we're doing in lower dimensions. So that's what these JS and JTs are. But then once we've chosen those JS and JTs, then we have a new J term on F, as in the previous slide. And when we substitute in the reflexivity terms, we'll get back our term F. Okay. So this works very well in all the examples that I've talked about, and these homomorphism types, they capture the identity types in the type theory setting, but in general, they capture things like Hom profunctors in the category-like setting. in spans, the Hom types will actually be really boring because they'll just be the trivial spans, which are identities on both legs. So that was the first part where I introduced a structure that captures in the setting of globular multicategories what it means to have homomorphism types. So in this second part, what I'd like to show you is how we can start off with one of these globular multicategories with homomorphism types and construct higher categorical structures. And there'll be two types of sort of high categorical structure that we'll consider. On the one hand, if we look at a type inside a globular multicategory, then we would expect that type to behave like some kind of weak higher category. So the types in a type theory behave like weak omega groupoids. So, on the other hand, if you look at the collection of a whole bunch of types and terms, then that whole collection itself should behave like some kind of weak higher category. But this is not like a higher category inside the type theory, it's the higher category that the type theory itself is. So, we're used to thinking of models of homotopy type theory as infinity one topoi. So this is that kind of result. So we'll get some results in both those senses. So first internally, and the key observation that I'd like to make is that the theory of globular multicategories with homomorphism types is essentially algebraic. And so this adjunction that we then have is actually going to do a lot of the work. So there's a category that I've called globular multigraphs that are basically just pre-sheaves on the shapes that I've been drawing throughout all these slides. So there's a category of those shapes, and then we look at pre-sheaves on those shapes. And every globular multicategory has an underlying globular multigraph, which is just the shapes that we use. And by abstract nonsense, there's going to be a free forgetful adjunction between these two categories of globular multicategories with homomorphism types and globular multigraphs. So let's see how this is useful, first in the case of zero types. So,
sorry, but the adjunction is non-monadic.
I don't know. It doesn't matter.
Okay.
I would think it is. Okay, so a zero type. If we start off with a zero type in a globular multicategory, then now viewing that globular multicategory as a pre-sheaf, we can use the Yoneda lemma and say that actually a zero type is the same as an arrow from the generic zero type, which is just the pre-sheaf that just has a single point. But now by adjointness, that's going to correspond to an arrow that starts off with the from the globular multicategory of homomorphisms freely generated by the point. So we could say that FH of the point is the theory of zero types with homomorphism types. And a type in a globular multicategory with homomorphism types is precisely the same as a map from the theory of types with homomorphism types. And it turns out that this theory of zero types of homomorphism types is a normalized contractible globular operad. So we reobtained that result of Garner and Vandenberg's in this setting. Every zero type has the structure of a weak omega category in any globular multicategory with homomorphism types. Okay, let's try and generalize this observation here to a more not just to FH of the point, but to more general things. So a brief interlude, we can demand an extra property of our homomorphism types, which says that they are strict in some sense. So what this says is that the various J terms that we can construct are always going to be not just equivalent, but actually equal. Another way of saying this actually is that the property defining J term says that substituting in reflexivity terms defines some kind of injective equivalence. And for the homomorphism types to be strict says this isn't just like a weak notion of injective equivalence, it's actually an isomorphism of omega categories, strict omega categories. And in general, what happens when we have strict homomorphism types is that the objects of our globular multicategories will now behave like strict omega categories. So they're strict omega category-like, as opposed to just omega category-like. So we have another adjunction by abstract nonsense. And now, using this adjunction, we can look at the unit of that adjunction to compare the three weak homomorphism types on a globular multigraph to the three strict homomorphism types on the same globular multigraph. There's a canonical map, and all it's going to do is introduce some extra equations that make our theories stricter. And it turns out that this map is actually always an acyclic fibration. And in this case, the correct notion of acyclic fibration is to look at those globular multigraphs, those pre-sheaves. They're pre-sheaves on a direct category, so there's always like a canonical notion of acyclic fibration, which just says that whenever we have the boundary of a shape, then we can find a filler. A boundary of the shape at the bottom, that's what it is. Yeah. So this unit of this adjunction is always actually an acyclic fibration. And it turns out in the particular case that X is the point and the bottom globular multicategory here is actually a globular operad, this result actually tells us that the top operad is contractible.
Can I actually ask a question?
Yep.
Just about that last result. Mm-hmm. Is it difficult to prove? Or does...
It's not. None of this is really too difficult once you've stated it right. Okay. You do need, as far as I can see, like this unit on three objects. At the moment, my proof is quite explicit. So I should say I should have said this at the start of the talk. This whole talk is based on a paper which should be up on the archive in the next couple of days once it's finished being processed, which is going to say all of this in much more detail.
Okay, great. I'll have a look at the...
Okay. So the example that I just said very quickly is that if we start off with the point, then the three theory on the point with strict homomorphism types is actually the same as the terminal globular operad. And this is very easy to see actually, because if we start off with any term in this theory, then we can always substitute in reflexivity terms and get back down to something really just the point or an identity on the point. And conversely, given any shape of pasting diagram that's the source of a term in here, we can always find some term with that shape in this operad using the J terms. But more generally, what will happen is we'll have a kind of span that looks a bit like this in the middle. So if I is some globular multigraph, then there's a span whose left leg is an acyclic fibration that strictifies our theory, and whose right leg is some kind of map into some arbitrary globular multi-category homomorphism types. So this example that I've listed on the slide, I've let I be the generic zero term. So that's really the globular theory that just has an arrow, nothing else. We then freely add homomorphism types, and by adjointness, a map from the theory of arrows of homomorphism types into X is the same as an arrow in X. And then using this result, we always have a kind of span like this. I mean, if this kind of map looks familiar to you, then this is a fairly standard kind of notion of a weak map from actually the strictification. So we can think of this result as saying that the zero terms in X are the same as weak omega functors. Okay, and in general, we can play this game for all the different representables, and we'll see that the n types behave like weak higher profunctors, and the n terms are transformations between them. Okay, so that was the internal part. Is everything clear so far before I go on to the external part? Okay. So now what we want to do is we want to combine all this internal data and construct some external higher category. So what we're going to do is we're going to look at the theories with just a point, just an arrow. There's also a shape of globular multigraph. Actually, I'm lying a bit. These should be reflexive globular multigraphs, which are, you can think of them as transformations between two arrows. So there are these kind of terms here that I mentioned earlier that behave like natural transformations. So they take in an object of A, and then they output an arrow in B. So these are natural transformations. Precisely these terms that are of this form. Okay, and then we can keep going on, and we can look at transformations between those transformations, and those are going to behave like modifications, actually. And if we look at the collection of all the types, the terms, the transformations, the modifications, and so on, what we would expect is that we'd end up with a weak omega category, and indeed we'll prove that that's the case. So that will be our external result. So just to fix some notation, if we define I to be this globular object, so the zero part is this are the points, the one part are these arrows, and the source and target maps are, they pick out the previous diagram, the previous shapes. And that defines a globular object in, it's actually a co-globular object in the category of globular multi-categories. Whenever you have a globular object in a globular multi-category, then you can always ask, what is the endomorphism operad? So we have an endomorphism operad and FH op I in the category of globular multi-categories. Actually, I think maybe we're missing an op here. And similarly, we can rather than looking at starting off with these shapes and adding weak homomorphism types, we can add strict homomorphism types, and we'll end up with an endomorphism category, an endomorphism operad in the category of globular multi-categories with strict homomorphism types. So quite an interesting result, I think, are these next two. So maybe I'll go down. Oh, okay, let's do them as they're listed on the slide. So firstly, the theory of strict arrows inside a globular multicategory of homomorphism types. It turns out that that theory is the same as terminal globular operads. It's the same as the terminal globular operad. So the way you can see that is if you want to understand what terms inside this this globular operad are, they're really homomorphisms of strict omega categories that tell you how to pick out composites. You sort of get there quite a roundabout way because we started off in this framework of globular multicategories. But because we're only looking at globular multicategories where sort of there isn't, there aren't any interesting 1 types or 2 types, those globular multicategories turn out to behave just like strict omega categories. And so the maps in these endomorphism, the terms of these endomorphism operads turn out to be what you might call, though there are various names, you might call them the active maps in the theta category or the generic maps in the theta category. That's basically what the terms are. And their source is always going to be a representable because this is a globular multicategory. So when you notice that, it follows that actually this is a very abstract way of saying that the category of strict omega categories is a strict omega category. What I think is more interesting is that if you take the endomorphism operad of the weak theory, then there's a canonical homomorphism down into the strict theory. This is again induced by the strictification adjunction. And this homomorphism is actually an acyclic vibration. Again, okay, well, we're doing quite well for time, so maybe I will say a bit more about how you actually prove that. And really the way that proof works is that you realize that this globular operad, FHI, is a globular object inside the category of globular multicategories with homomorphism types. So we have a globular object inside some category. Now that category has a weak factorization system with our acyclic vibrations again being the acyclic vibrations in that factorization system. And it turns out that globular object is cofibrant in the sense that all its objects are cofibrant and all its boundary inclusions are cofibrations. So because that object is really nice and it's cofibrant, and also the strictification maps, as already proved for the internal case, are acyclic vibrations. What that lets us do is it lets us transfer this homotopy theoretic result from inside the globular multicategory to outside the globular multicategory. So we have well-behaved things inside the globular multicategory, and because they're well-behaved, we can combine them and get this nice homotopy theoretic property outside that says that the theory of arrows in a globular multicategory with weak homomorphisms projects down by strictification into the theory of arrows with strict homomorphisms, and that is an acyclic vibration. Okay, so immediate corollary is that this endomorphism globular operad is itself a normalized contractible globular operad. And so whenever X is a globular multicategory with homomorphism types, the collection of types and terms of that form that I was drawing in X is always, I don't know why I put globular there, a weak omega category. So that's our external result. And, we would expect probably a few more with the, organizing the collection of profunctors and so on, but I don't go into that into the paper. Yeah. So to summarize, if we start off with a collection of higher category-like objects, such as, for example, a type theory with identity types, or even presumably some sort of directed type theory, then there'll always be a globular multi-category with homomorphism types. You might want some semi-strictness conditions on the higher category-like objects, it's true. But once you have one of those globular multi-categories of homomorphism types, we're in a good place because we always know that its objects are in a very precise sense higher categories, its terms are always functors, its dependent types are always profunctors, and its higher terms are always transformations between those profunctors. And furthermore, like the collection of all types and terms is going to behave like a higher category itself in the external sense. So that's really all I wanted to say. As I said, there's a paper that should be appearing any day now once I finish wrangling with Archive, and that will cover pretty much all of this. A few of the examples are not covered in the paper, but the proof of all these results is all there. So thank you very much.
Okay, so thank you, Christopher, for the talk. We thank the speaker, and as always, we cannot clap. Oh, sorry, Christopher, still share your screen because maybe someone will want to ask questions.
Yeah, sure. I'm just. Yep.
Now, if anyone has questions for Christopher, that's a good moment to ask.
I just had a question about the. Do you show that the collection of strict omega categories gives rise to a globular multi-category? Is that right?
So that is. So I'm pretty sure of that result. That result isn't in the paper.
Okay.
I can construct something that certainly looks like it is that, but what I need to do is to compare that to existing models of strict globular multi-categories. And it shouldn't be too difficult to do that because there's a kind of universal property characterizing these homomorphism types, which is relates them to the monoids and modules construction of virtual double categories. So yeah, I mean, I'm pretty sure, but the details of that do need to be written out.
Okay, and is there any, what about something like, have you tried to show that quasi-categories, for example, can be put into a globular multi-category or anything? Does that?
Sorry, what's the question?
Well, so collections, so maybe I didn't understand it exactly right, but collections of higher category like objects give rise to globular multi-categories, right? Or,
yes.
So what if the higher category like objects are something like quasi-categories?
So yes, that's a good question. So in general, these homomorphism types are kind of as strict as the identity types in type theory. So there is some strictness properties here that we're going to need. Having said that, in something like the category of quasi-categories, there are well-known model structures. That it's well known how to get one of those and end up with a dependent type theory or something strict enough for that. So it should work for those too. Another result that I would like to prove actually is if we go back. Right. So what should be the case is that we can kind of mimic what Vandenberg and Garner do in their paper, but instead of starting off with a path object, we could start off with some kind of directed path object. So you'd have to make precise what a directed path object is. I have a pretty good idea what that should be because I can kind of work backwards, and it corresponds quite nicely to what Page North is doing. So that's also future work, and that would give you a model with quasi-categories.
Okay. And is it something like you just need to be able to, things like you need to be able to compose identities strictly or things like that?
it's like, I mean, you need strict, if you think about what a path object is, it's kind of as strict as that. Does that help?
Okay.
Yeah, I do agree. The problem is that because we're in a globular multi-category, there are lots of different things that you might call identities. And yeah, you're right, some of them, the homomorphism types should be kind of strict in some sense.
Okay.
But even the
I'll try and ask you again sometime in the future, maybe a bit. Or I'll look forward to the paper anyway.
Okay, great.
I have one question about your last slide.
Yep.
Yes, this one. I wanted to ask you if you have constructions in opposite direction, something like reconstruction theorems.
Yeah, so actually this relates very nicely to the previous question. What I believe is true, but this is starting to get, more sketchy, is that if you have a globular multi-category of homomorphism types, and it is span-like in some sense, so basically it's a category of spans, maybe restricted to two-sided fibrations, that then having homomorphism types should be the same as having directed path objects in some sense. And yeah, there are some promising results in that direction. That's as much as I can say.
So this is something like when you have something like an allegory and you take only a special kind of map and you recover the category you started from, or when you, yes, in some sense.
I can't think of a good analogy really. There's sort of I would argue that these globular multi-categories have been showing up as they do in the Vandenberg and Garner paper. They show up already, but typically when they show up, they've been constructed from some kind of type theory, as Vandenberg and Garner do. So they are constructed using some kind of category of spans. So it seems quite doable to categorize exactly when a globular multi-category is a category of spans. In other words, we would end up with a tighter correspondence between globular multi-categories of homomorphism types and directed type theories.
Thank you. And okay, so if we have no more questions, and it looks like that, so we thank the speaker. Thank you, Christopher, for coming today. And we are done for today. And I still haven't announced anything, and I think next week we will not have a talk. And I will keep you updated via the mailing list. Maybe I will send it also to you, Christopher. So thank you again for joining us, and thank you everyone for coming, and see you next time.